let's discuss white dwarf star. And before going into white dwarf star, let's see how a star stay in the stable state. In the star, fusion reaction takes place, and due to this fusion reaction, there is an outward force, and there is inward force due to the gravity. Gravity tries to collapse, and this fusion force due to this fusion reaction is in the outward direction. So both are in opposite direction, and both cancels, and the star stays in the stable state. And once the fuel is exhausted, this fusion reaction stops, and then the star moves into its evolutionary stage, the next stage, and it can either be a white dwarf, and it will be a white dwarf if the mass of the star is less than 1.4 mass of sun, and if the condition this mass condition is met, that is if mass of the star is less than 1.4 mass of sun, this will be a white dwarf star. The next stage of the star will be a white dwarf. Otherwise, it can be a black hole if the mass is greater than 1.4 solar mass. The star will undergo supernova explosion and it will turn into a black hole or into a neutron star. So this white dwarf star is one of the evolutionary stage of a star when the mass is less than 1.4 solar mass, and this limit is known as Chandrasekhar limit. And then again moving into white dwarf star, and also this white dwarf star is an application of Pauli's exclusion principle in the stellar context. There is no fusion reaction to stop the collapse due to gravity in white dwarf star, and due to the Pauli's exclusion principle, all the particles are not allowed to stay in a single state, that is the single lowest state. Due to Pauli's exclusion principle, all particles cannot stay in the single state, and therefore the lower states will be filled, then the particles are pushed into the higher states. Why the particles are pushed into the higher state? Because due to Pauli's exclusion principle, these particles cannot occupy the lowest state. എല്ലാ പാർട്ടിക്കിളിനും ഒരേപോലെ ലോവർ സ്റ്റേറ്റിൽ എക്സിസ്റ്റ് ചെയ്യാൻ പറ്റത്തില്ല, ബിക്കോസ് it is against Pauli's exclusion principle. And then the condition for degeneracy Fermi-Dirac gases melt, particularly the strong degenerate Fermi-Dirac gas. All the conditions are met in white dwarf star, and there is this electron gas in the white dwarf star is a strongly degenerate Fermi-Dirac gas. It is having energy E0 and pressure P0, the degeneracy pressure, and this degeneracy pressure opposes the gravitational collapse. And in that sense, this is a application of Pauli's exclusion principle in the stellar context using the Fermi-Dirac statistics. Then we can move on to the white dwarf star. And the content of white dwarf star is helium, and mass is 10 raised to approximately 10 raised to 30 kilogram, that is equal to mass of sun. And then density of white dwarf star is 10 raised to 10 kilogram per meter cube. That is, it is highly dense and the temperature is approximately 10 raised to 7 Kelvin. And what is the condition for Fermi-Dirac gas to be strongly degenerate? The temperature should be less than that of the Fermi temperature TF. That is the condition for degenerate Fermi-Dirac gas, particularly highly degenerate Fermi-Dirac gas. The temperature should be very much less than the Fermi temperature. So this is the temperature of white dwarf star. Then we need to know whether it is very much lower than the Fermi temperature. To calculate TF, the equation is EF, Fermi energy by K. So we need this Fermi energy. And Fermi energy is, we know, that is equal to h square by 2m 3n by 8 pi v raised to 2 by 3. And this depends upon n by v. Particle density ആണ് depend ചെയ്തിരിക്കുന്നത്. And here this white dwarf star is highly dense. Substituting the density, we get this is equal to 20 million electron volt. Then divide by K, we can find TF. And TF is found to be 10 raised to 11 Kelvin. So 10 raised to 7 Kelvin is very much less than 10 raised to 7 Kelvin is the temperature on white dwarf star, and that is very much less than the Fermi temperature in this case. Like Fermi temperature എന്ന് പറയുന്നത് ഡെൻസിറ്റിയെ ഡിപ്പെൻഡ് ചെയ്തിരിക്കുന്നു. അപ്പോൾ ഡെൻസിറ്റി ഇറ്റ് ഇസ് ഹൈലി ഡെൻസ്. അപ്പോൾ നമ്മൾ കാൽക്കുലേറ്റ് ചെയ്തതിൽ നിന്നും TF is 3 raised to 11 Kelvin. That means the temperature is very much less than 10 raised to 11 Kelvin, and this Fermi-Dirac gas is in a highly degenerate case. Now we are going to calculate E0. E0 is integral of EPS GP/dP. GP/dP is the number of particles in the momentum range P to P plus dP. Number of particles in the momentum range P to P plus dP, that is GP/dP. And single particle energy, the energy is the relativistic energy. Since the temperature is high, the energy is the relativistic energy, and we know the relativistic energy is E square is P square C square plus M square C raised to 4. That is E is root of P square C square plus M square C raised to 4. And GP/dP, we already know that is equal to 2s plus 1 is the spin degeneracy into V 4 pi P square dP by h cube. So substitute the GP/dP value here, and we know for electron S is equal to half. 2 into half plus 1 is 2. 2s plus 1 is 2. Substitute this value for GP/dP. Here left side it is E0. So we will be getting the value for E0 as E0 is 2V by h cube 0 to Pf P square C square plus M square c raised to 4 raised to 1 by 2 4 pi p square dp. This integrating element is dp, so here the limit is up to pf, because we know the energy at the lower energy, the state below ef is filled. The maximum filled state is ef, അല്ലേ? ടി ഈക്വൽ ടു 0 കെൽവിൻ അല്ല, ടി ഈക്വൽ ടു 0 എന്ന് പറഞ്ഞാൽ ലോ റേഞ്ച്. ഇപ്പോൾ ഇവിടെ 10⁷ കെൽവിൻ എന്ന് പറയുന്നതും വളരെ ലോ ടെമ്പറേച്ചറാണ്. സോ ലെവൽസ് അപ് ടു ഇ എഫ് ഈസ് ഫീൽഡ്. ഇപ്പോൾ ഇവിടെ ഇൻ്റഗ്രൽ എലമെൻ്റ് എന്ന് പറയുന്നത് പി ആണ്. പി എഫിന് കറസ്പോണ്ടിങ് ആയിട്ടുള്ള പിയുടെ വാല്യൂ, ദറ്റ് ഈസ് പി എഫ്. പി എഫ് ഇസ് upper limit here. And PF and energy are related as P is equal to root of 2mE. That is, PF is root of 2m EF. That is equal to 2m into EF is h square by 2m. 3n by 8 pi v raised to 2 by 3. And root of h square is h. This is h into 3n by 8 pi v. Root of 2 by 3, that is 1 by 3, and that is equal to pf. And we have to integrate this equation number 1, to find E0. For that, take P by MC. P by MC as x. For the ease of integration, let us denote x P by MC by x. That is, dP by MC is dx. Then substitute in equation 1, and we get E0 is 8 pi v m raised to 4 c raised to 5 by h cube 0 to, now limit is to xf. നമ്മൾ എക്സിൻ്റെ ടേംസിലേക്ക് മാറ്റി 1 plus x raised to x square raised to 1 by 2 x square dx. And let this function be f of x. Pressure, we know it is equal to minus dou E by dou V. ഇപ്പോൾ ഇതിൻ്റെ ഡീറ്റെയിൽസ് എല്ലാം ഫസ്റ്റ് യൂണിറ്റിലാണുള്ളത്. And that means P0 is minus dou E0 by dou V. So we have to differentiate this E0 with respect to V. V ഡിപ്പെൻഡ് ചെയ്യുന്ന രണ്ട് ടേമുകളാണുള്ളത്, ദിസ് വി ആൻഡ് എഫ് ഓഫ് എക്സ് എഫ്. അതർ ക്വാണ്ടിറ്റീസ് ആർ കോൺസ്റ്റൻസ്, ദറ്റ് ഈസ് P0 which is equal to derivative of E0 with respect to V into the negative sign. This is minus 8 pi, the constant terms, m raised to 4 c raised to 5 by h cube dou by dou v of the product v into x raised to 5. So here there are two terms. So first term v into dou xf by dou v plus dou xf by dou v into v. Here this is function of xf. Second term എന്ന് പറയുന്നത് function of xf and this f of xf. So this is 8 pi m raised to 4 c raised to 5 by h cube minus v dou v by dou v, that is 1 into f of x5 plus v into derivative of f of xf, that is dou f by dou xf by dou xf into dou xf by v. Because f of x5 will direct at v illa. f of x5 is connected to v through xf. f of xf എന്ന് പറയുന്നത് xfൻ്റെ ഫംഗ്ഷനാണ്, and that xf, there is the term v. So dou xf by dou v എന്ന് പറയുന്നത് dou xf by dou xf into dou xf by dou v. That is the second term. So we need to find this dou f of xf by dou xf and this dou xf by dou v. f of xf എന്ന് പറയുന്നത് ഒരു ഇൻ്റഗ്രൽ ആണല്ലേ. It is an integral. Then take derivative with respect to xf 0 to xf x square into 1 plus x square raised to half dx. So there is the derivative and this integral. In total this is equal to xf square into 1 plus xf square raised to half. That is system dou xf by dou xf. Then we need to find dou xf by dou v. xf ഉം v ആയിട്ടുള്ള റിലേഷൻ. xf is pf by mc and pf is h into 3n by 8 pi v raised to 1 by 3 by mc. അപ്പോൾ പി എഫിൻ്റെ എക്സ്പ്രഷൻ, അതായത് h into 3n by 8 pi v raised to 1 by 3 substitute here, then xf, then take the derivative dou xf by dou v. Then we get this term dou xf by dou v, this dou xf by dou v. And therefore p0 is 8 pi m raised to 4 cf, and we have multiplied this minus 1 by 3 xf cube 1 plus xf raised to 1 by 2 minus xf. And this is p0. And then we are going to calculate the value for m0. For that we have to relate p0 and m0. m0 മാസിൻ്റെ ലിമിറ്റാണ് നമ്മൾ കാൽക്കുലേറ്റ് ചെയ്യാൻ പോകുന്നത്. p0യിൽ നിന്നും m0യുടെ എക്സ്പ്രഷനിലേക്ക് എത്തണമെങ്കിൽ we need to do some steps, and for that let's see what is the relation between this mass, radius and this pressure. And this white dwarf star is mainly composed of helium atom. Helium atom is having 2 protons, and protons are the heavier particle. ഇലക്ട്രോണായിട്ട് കമ്പയർ ചെയ്യുമ്പോൾ ഹെവിയർ എന്ന് പറയുന്നത് പ്രോട്ടോൺസ് ആണ്. So neglect the mass of electron. Main contribution for mass is from this proton. So each helium atom 2 proton. So if there are n helium atoms, the total mass, the approximate total mass is 2 mp into the number of helium atom, 2 mp into n. And considering this as a sphere, the volume is 4 by 3 pi r cube, and this is the total mass of star m. Then find V by n. V by n will be, volume is 4 by 3 4 by 3 4 by 3 pi r cube divided by n. From here n is m by 2 mp, m by 2 mp, and this is v by n, and this is equal to 8 by 3 pi mp r cube by capital M. And then relate this v by n to p. Momentum v by n ആയിട്ടുള്ള relation that we know as pf. pf is h into 3n by 8 pi v raised to 1 by 3. ഇപ്പോൾ ഇവിടെ v by n ഉണ്ടല്ലേ, v by n ൻ്റെ ഇൻവേഴ്സ് ഉണ്ട് ഇവിടെ, n by v. സോ സബ്സ്റ്റിറ്റ്യൂട്ട് v by n, അതിൻ്റെ ഇൻവേഴ്സ് എടുക്കുക, ഇതിലേക്ക് സബ്സ്റ്റിറ്റ്യൂട്ട് ചെയ്യുക. ദെൻ ഇറ്റ് വിൽ ബി ഈക്വൽ ടു h by 2 pi r 9 pi by 8 m by mp raised to 1 by 3. And x is p by mc, or xf is pf by mc, and that is equal to h by 2 pi mc by 9 pi m by 8 mp raised to 1 by 3. So this can be equal to m raised to 1 by 3 by r, taking this as a 2 pi mc by h as r bar, and this 9 pi m by 8 mp as m bar. This xf is equal to m bar raised to 1 by 3 by r bar. So that is the relation between this m bar, r bar, and this xf. And xf is related to pf, and this pf is related to n by v. So these are the relations. Then we find the gravitational self-energy. The gravitational self-energy means the energy required to form the star into that particular radius. അപ്പോൾ ആ ഒരു റേഡിയസിൽ അപ്പം അങ്ങനെ ഒരു സ്റ്റാർ ഫോം ചെയ്യണമെങ്കിൽ ആവശ്യമായിട്ടുള്ള എനർജിയാണ് ഗ്രാവിറ്റേഷണൽ സെൽഫ് എനർജി. നമ്മൾ ഇലക്ട്രോസ്റ്റാറ്റിക്സിൽ ഒരു പെർട്ടിക്കുലർ കോൺഫിഗറേഷൻ്റെ പൊട്ടൻഷ്യൽ എനർജി കാൽക്കുലേറ്റ് ചെയ്യും അല്ലേ. ഇൻഫിനിറ്റിയിൽ നിന്ന് ആ ഒരു പോയിന്റിലേക്ക് എ ബി സി ഡി എന്ന സ്ക്വയറിൻ്റെ 4 പോയിൻ്റ് ആണെങ്കിൽ ആ സ്ക്വയറിലേക്ക് എത്താനായിട്ട് എത്ര എനർജി വേണം എന്നുള്ളത് നമ്മൾ ഇലക്ട്രോസ്റ്റാറ്റിക്സിൽ കാൽക്കുലേറ്റ് ചെയ്തിട്ടുണ്ട്. സോ ലൈക്ക് ദാറ്റ് ഇൻഫിനിറ്റ് ഡൈലൂഷനിൽ നിന്ന് ഇങ്ങനെ ഒരു സ്റ്റാർ ഫോം ചെയ്യാൻ വേണ്ടിയിട്ടുള്ള എനർജിയാണ് ഗ്രാവിറ്റേഷണൽ സെൽഫ് എനർജി. ആൻഡ് ദറ്റ് ഈസ് ഈക്വൽ ടു minus 3 by 5 g m square by r. And the work done to form this star of radius r from the state of infinite diluteness, this work done എന്ന് പറയുന്നത് ഫോഴ്സ് ഇൻറ്റു ഡിസ്പ്ലേസ്മെൻ്റ് ആണ് വർക്ക് അല്ലേ. ഫോഴ്സ് ഇൻറ്റു ഡിസ്പ്ലേസ്മെൻ്റ് ആണ് വർക്ക്. ആൻഡ് ദിസ് ക്യാൻ ബി റിട്ടൺ ആസ് എഫ് ബൈ എ ഇൻറ്റു ഡി ആർ. എഫ് ബൈ എ എന്താണ്? ഫോഴ്സ് ബൈ ഏരിയ ഇസ് ദ പ്രഷർ, ആൻഡ് ദിസ് ഇസ് ഏരിയ ഡി ആർ, ആൻഡ് ദിസ് ഇസ് ദ dW, and the work done is 0 to R. Pressure. Here the pressure is the degeneracy pressure P0. It is spherical, so the surface area is 4 pi r square dr. And on integrating, this is equal to P0 4 pi r cube by 3. That is the integral. And equate this to minus 3 by 5 gm square by r. Then to omit this negative sign, differentiate both sides. Minus 3 by 5 into gm square by minus 1 by r inde minus sign ഉണ്ട് 1 by r ന്റെ ഡിഫറൻഷ്യൽ എന്ന് പറയുന്നത് minus 1 by r square അല്ലേ. So this minus and minus will be cancelled, and this is equal to P0 by 4 pi by 3. Right side ne differentiate ചെയ്യുക, r cube ne differentiate ചെയ്താൽ 3r square. On rearranging the expression, P0 is 3 by 20 pi g m square by r raised to 4. And so we have this P0, then the relation between m, r and xf. Then we have the expression for f of xf. Using all these relations, we can calculate m0, and m0 is calculated as 1.4 the mass of sun, and below and above this limit, that will be a black hole or a neutron star. The star finally explodes, and that will take an enormous amount of time. അപ്പോൾ അതൊരു ചെറിയ കാലയളവല്ല, ഒരു വലിയ ടൈമാണ്, വലിയൊരു ടൈം ഡ്യൂറേഷനാണ്. ഈ ഒരു സ്റ്റേറ്റിലേക്ക് ഇതെത്താൻ വേണ്ടിയുള്ള ടൈം ഡ്യൂറേഷൻ എന്ന് പറഞ്ഞാൽ ഇറ്റ് ഈസ് ഇൻഫിനിറ്റ്ലി ലാർജ്. And this is the Chandrasekhar limit, that is, if the mass of the star is less than 1.4 the mass of sun, the star will be a white dwarf star. അപ്പോൾ അതിലേക്ക് എത്തുന്ന ഇക്വേഷൻസ് ആണ് നമ്മൾ ഈ എക്സ്പ്ലെയിൻ ചെയ്ത ഇത്ര ഇക്വേഷൻസ്. And this is the application of Pauli's exclusion principle in the context of this stars using Fermi-Dirac gas, particularly the highly degenerate Fermi-Dirac gas.